Okay, I think we are 5 minutes behind, and I wanted to show something. So maybe I'll briefly describe that, and we can get into the talk. And the news for this week is coming out of California. Where did we miss that?
It doesn't matter how tall the building is.
Okay. Let's skip the ad. So I guess you've been following the news. There has been a drought declared in California for a while now, and I just wanted to show a brief. It's a 4-minute video, I think, that covers maybe not the entire topic, and it doesn't provide any solutions, but it does give you some sense of what the issues are and how many different actors are involved in this. So we'll skip over to the video.
These dry times, this drought is got a far-reaching impact. It may go well beyond California. Yeah. I mean, we've never seen anything like this before. We just don't know. Normally, we'd have green grass enough to sustain all these cattle and more. You'd have green grass here on the hillsides, anywhere from 4 to 8 inches tall, and we wouldn't be feeding hay. If it doesn't rain, we know this, it's not going to be good. We sold over 100 head of cows, so we sold roughly 20% of our cow herd. We keep waiting and hoping that we're going to get a rain and we won't have to sell any more, but we have some earmarked to go to town if that has to happen.
And there's more than just a lack of rainfall to make John angry. Not everywhere in California is this dry. This is the Imperial Valley, where the All-American Canal turns desert into Eden.
The long-term solution is let the capitalistic system figure out the balance of water. And the water, they used to say water used to only run downhill. Well, that's not the case. Water runs uphill real easy with enough money pushing it. About a quarter of the valley is grown in alfalfa, and about 30% of the alfalfa grown in the Imperial Valley is used for export markets.
The fastest growing market is China. The alfalfa hay is compressed into smaller bales, wrapped for transit, and loaded into containers. America's trade imbalance with China means many of these go back empty. Filling them with hay makes it cheaper to move alfalfa to Beijing than to John, a few hundred miles away in the Central Valley.
That's what we're doing. We're just virtually exporting our water.
You'd love to have the hay at a cheaper price up here.
Absolutely. Absolutely. I mean, we compete with the dairies in California. They set the price. We're always a little resentful of the dairy farmers. But that's nothing compared to the resentment we feel when hay is exported overseas, when it could stay right here at home and be utilized.
In my opinion, it's something that's part of the global economy. If we want cheap cars and cheap TVs from China, we have to do something to balance that trade imbalance. And it's our thought that alfalfa is just a small part that we can do in Imperial Valley agriculture, in the state of California agriculture, to try to manage that trade imbalance. If I didn't produce the alfalfa, if I didn't use the water would be going to another use. The cities use 70% of their water to irrigate their lawns, to irrigate the golf courses. So if you talk about inefficiencies, is it more efficient to use water for a golf course, for the movie stars, or is it more efficient for 120 farmers to use it to grow a crop and to export it and to create this mass economic engine that drives the country?
I think we need to think about what we're doing with our resources. I realize that the planet is almost all capitalistic. But we need to start thinking about other things besides making a dollar.
Hey, I just wanted to say one thing about that because my kids are saying, "Oh no, don't talk about those California happy cows." The California happy cows. I mean, half the irrigation water in California, when they don't talk about marijuana, but half the irrigation water is going to grow alfalfa. That's paid for, almost all that water is paid for by the federal, us, the federal people, through our federal taxes.
That's the other issue, right?
And the amount of water that goes to the farmers for irrigation is huge compared to the amount that goes to the cities and towns. It just overwhelms it. So it's just like, okay, reduce the alfalfa by 10%, you can meet a lot of the demand. But the other thing that, which is complicated, is the reason they have those cows
make
that
it go
they're feeding
forward.
the
Do I still
alfalfa
do
to is because of the milk marketing laws in the United States.
Right.
So it's not like you need to produce milk in California, because it's much more efficient to produce milk in Michigan and in New York and in New England. But where you're not allowed to sell milk from one state into the next in the United States. So all the milk that's consumed in California has to be produced in California.
Yeah.
Because of laws that were established 100 years ago. So it's in my mind, when we talk about sustainable agriculture and environmental agriculture, these are the real things we're talking about, not about fertilizer. It's about the system that just is not environmentally rationalized. And so then you get hugely poor use of water. It's what it ends up being. So.
And it seems like it's not just about water anymore. There was trade war with China, Czech.
Yeah,
There
that
was
was interesting.
Conflict between agriculture and urban societies,
Right.
Czech.
And dairy.
And
Dairy and the beef
Right.
farmers, yeah.
And they're talking about two different locations in California. So the Imperial Valley is the southern part of California that gets the water from the
Right.
Colorado River Basin. But then the northern part, which is the Central Valley, is getting its water from, essentially California itself.
Yeah,
So there are two different systems, and they were trying to compare how they are faring differently
yeah.
in this system. And connection to today's talk, maybe in some way, is all of that is possible because of these huge canals. In some ways, grand ditches,
We'll get
which
to there.
move the water from one place to another, essentially into these deltas where much of the farming is happening, and all our fruits and vegetables are coming. So with that, I want to segue into today's talk by Dr. Rebecca Schneider. She is an associate professor in the Department of Natural Resources here. She works on ecological ways of sustainably managing water. There's a lot of buzzwords in there, so I'm sure she can talk about a whole lot of details. Her work is not restricted to just New York. She has worked in Western US, China, Eastern Europe, and a whole lot of other places. So she can maybe talk about how that interacts with
No, I'm not
work here.
going
No, only talking about ditches here.
Today's ditches. Although I do have one.
All about ditches, and we can maybe learn something in detail about how these ditches are different from the ones we saw in the video.
Okay.
All right.
All right, guys. So maybe that was a great video to show because the more everywhere you look, you see nothing but like bad news. And I'm all about solutions and being positive and let's find ways to deal with this. And that's what this talks about. All right. So I'm putting it in the context of climate change and this really growing water scarcity. And then I don't actually get often a chance to talk to scientists. And so I'll go into more detail about the science that I usually get to. Usually I'm talking to highway guys and so it's kind of like a treat to get to talk to this in a little more detail. And then I'm going to talk about what we're doing to actually get this applied. All right, so that issue of drought, and actually right now, as I was talking about, they said it's a 1 in 500 year drought. I mean, if you've been watching what's happening in California, it's pretty phenomenal. But I'm going to actually just focus now on 2012 because back then in 2012, just 2 years ago, we were having a severe drought in the Midwest, and Iowa farmers were trying to grow corn. I actually know somebody whose father had a farm and said, "That's it, I'm leaving," and they sold the farm because it was so severe. But what people keep forgetting is this was 2011. The same area was flooded severely. This is gauges with major flooding, purple, gauges with moderate flooding, red. The same area that had a drought the next year had flooding the year before. And that to me is the good news because the truth is we have in many places, now California's not really it, but in lots of places, what we're having is lots of rain and then dry. We have water and then we get rid of it. It's gone and you don't have it later. So my mantra is, look, we have to start learning to save the rain for a sunny day. And really, for hundreds of years, our strategy for dealing with flooding, race it out of the system, channelize rivers, put up levees, drain wetlands, get rid of it as fast as we can. And now it's like, maybe we need to rethink that strategy. And segue to the key part of this all is that humans, this increasing water scarcity, humans have done a lot of the problem, have caused a lot of the problem. And in terms of, and in that we have done what's called a crisis in water management. The Fourth World Water Forum, I think it was about 3 or 4 years ago or 5 years ago, said we have a crisis in water management. And what it means is we've done a really bad job with the water that we have. And the way I like to think of this piece of it is that this is the cross section of a watershed. You only get, and it's a bowl, you only get as much rain as falls in your bowl. It's a finite, relatively knowable amount. And what happens to it is pretty well easy to follow and figure out. It comes in, and if you have a hard surface like a parking lot, it runs off, and that ends up in our lakes, our streams, and finally the ocean. But if you have a porous surface, water infiltrates, goes down, hits something like bedrock, begins to fill up, that's groundwater, and that moves sideways and ends up in streams and lakes and rivers. And that's basically the two dominant processes. Now, evapotranspiration is really key. It's the rest of the cycle. And basically, from the Mississippi West, it dominates things. And for us, it's getting to be a lot more important with climate change. But really, until recently, these were the two big processes. And as Todd nicely set up last week, it's a balance, all right? You have one or the other happening. The rain comes in, you have a knowable amount. And pre-development, much of the Northeast looked like this. Just forested landscapes, deep organic soils, highly porous. And so largely, water didn't go to runoff. It went deep into groundwater infiltration. And what we've done is shift that balance away from that with lots of impervious surfaces, burning off the organic matter, getting it eroded. And basically, we shifted it to be largely runoff. We did that. Now that's the good news, because it's going to be very tough to control where rainfall occurs on global scales. But this, we can control how much rain runoff occurs. How much do we get rid of? And that to me is, oh, we can change that. So this issue of how important stormwater runoff is has gained, a lot of attention. And the EPA Phase 2 stormwater regs went into effect in 2003, largely to focus on pollutional, but also to deal with flooding. And that's where the green infrastructure came in. They said, look, you can't have, this is actually Route 89 over in Ulysses, putting up this house, and it's all this sediment's running on. It was a mess, all right? And that was the intent, to say we can't have stuff like this happen. We're going to put a giant development in. I'll think of all the crud coming off. And so the whole issue of infrastructure, water infrastructure, this is what we're trying to do with, they were hoping to do, an unfunded mandate, but things like rain gardens, permeable pavements, infiltration basin, that's down in White Marsh, Maryland. All these different strategies to keep water up on the development, where the development occurs, and not letting it leave the landscape. Income, here we come in, roadside drainage networks. So I actually got into this because I'm an ecologist, so I'm interested in what's happening in streams, and like, why is all this erosion going on? So let's start looking at what these ditches are doing. And so the question was, what role do they play in floods, in droughts, and water pollution? And that was our kind of starting point. So this has actually been going on, and I don't often get to sit, and I actually got to make a nice little slide of it all. This work actually started in 2001 working with undergrads for a couple of summers trying to figure it out. We were mapping Infill Creek and looking at bed load. Then we got some faculty involved and got several grants, and the key players have been, Todd Walters has been absolutely critical in all this, and David Orr over in Local Roads. And then two key graduate students who did a ton of work, Kim Falvo and Brian Buchanan. And it continues on. We had a grad class last spring looking at issues of barriers to ditch adoption, and we put in some grants with people, and definitely it's evolved, and here we are down here, and I'll talk about that some more. But it's a nice evolving, growing process with different people coming and getting engaged, and it's been really good. And I don't even have all the town highway guys and other people who have helped out in that realm. And then from Extension as well, we have this is simultaneously building people's awareness. We want people to do this. And so building awareness and identifying BMPs, so that's been going on simultaneously. All right, just so you know, as you get into this, you starting to realize this is worldwide, okay? So I have thousands of photos of ditches, and I get people to send me photos of ditches. So this is a ditch in Ethiopia, and one of our graduate students actually was there and was starting to realize how much gullying and erosion is due to ditches. This is us up here. This is northern China where we're working, and the ditches are all over the place. And this is actually an ancient ditch from in Mexico. And the point being that 50% of the contiguous U.S. is within 382 meters of a road, And road densities on average, one measure said 1.4 kilometers per square kilometer. Basically, roads are everywhere, and road ditches tend to go with them. So what we've been doing over this long period of time is we're now into 7 different watersheds, all central New York. Some drain down to the Chesapeake, some drain up to Lake Ontario. And we do basically the same kind of things and everything. The first thing you have to do is map the ditch network, the network of ditches that crisscross the watershed. And you have to actually, what are their lengths, what's happening in the bottom of the ditch, what's management, how's it being managed, and where do they connect the streams. And this is actually from Paynes Creek that Brian Buchanan did, so you actually see here it is the creek system naturally, so that's the natural stream channel system, and this is where all the ditches interface with it. And you can do some of this with LiDAR and get pretty high resolution, but the reality is, the bottom line is where the ditches dump into a stream. And it's wherever the highway guys decide, oh, I would take it and dump it, and they're not. I haven't found a way that you could do this remotely. But I mean, we actually walked the Trimble, there it is, that's where they dumped it. And sometimes it's miles of ditch, and oh, there it goes into the stream. So it's kind of you can do a lot of estimation from roads alone, but you're not really getting, if you really want to get down to the key point, it's where they dump in. Then we're interested in, well, what's happening in the ditch? So we use True Tracks to monitor total water flow and ISCO samplers, because sometimes these are storm driven. If a storm occurs in the middle of the night, you don't know it, you do them catch it. So the ISCOs allow us to get suspended sediment, dissolved chemicals. And the key part that we don't have as much as I want yet, but some, is bed load. And that's the heavier stuff that doesn't get carried in suspension, but it bounces along the bottom. We started out using small buckets. We've gotten bigger and extensive. We're trying to capture how much bed load moves through the system. This is an example. So some ditches are vegetated, herbaceous, but this is what they look like kind of when they scrape them. So highway guys clean, they call it cleaning. They didn't like when I said scrape. Clean the ditches about once every 4 years. It depends and varies how often, but that means at any given time, about 1/4 of the total system is sitting there scraped, unless they hybrid seeded after, which doesn't happen all the time. And then we did some modeling. This is Brian did some of it, Kim Felber did some others of it, trying to understand how these changes in the ditch network translate into hydrology in the system. So what have we found? So the mapping part started to get a handle on how critical or how much they're affecting it. So of all the 7 watersheds we've looked at, on average, they're about 42 square kilometers in length with 54 kilometers of road. And that's less than 1% of the surface area. So even though when they design them, they're thinking about water hitting the road and running into the ditches on the side, there's about 81 kilometers of ditches, all right, of which 51 on average are connected. So some ditches aren't even connected to streams. But they connected 94 locations in this small watershed, 42 square kilometers, 94 different places ditches dump in. And actually, the area of the basins that connects to that actually drains the ditches is about 22%. So a ditch doesn't just capture the water that hits the road and rolls off the side. If there's a big hill slope, well, it's actually capturing that runoff too. So the drainage basins, I'll show you a picture in a minute, are really key, all right, to what's happening. It's the drainage basins leading to the ditches. Stream channel. So the stream channel is the natural system for draining the land. And there's a measure called stream channel density, and without ditches, it's about 1.5 kilometers per square kilometer. But because of all these attached ditches, on average, it's 2.73. We've had it up to 4 or greater in some of the watersheds. So it really basically effectively increases the length of all the stream channel system, increasing the connectivity between land and water. So this is just, actually I use it for like when I talk to highway guys, but this is the Doolittle Creek watershed. There's the watershed divide. The dark lines, the blue is the creek system, and the red is the actual, and this is a very forested catchment, is the road system. And basically, what's happening is all these are the basins that potentially drain into the ditches, the brown part. That's the 22. So on average, 22% of every watershed that we looked at drains to a ditch, okay? Now, we'll see why that's important in a minute. And I put these little faucets here because one of the deals is that it really concentrates flow shoots it into the stream like a high velocity faucet. But note this one here, and this is really important. See this little basin, and here's this natural stream right here. When it rains, that's a hill. So normally when it rains, it would hit the surface and move its diffuse flow down the hill slope and enter the stream all along this line here, okay, slowly over time. But what happens is this ditch is right here. It short circuits the entire system. Captures, you're going to see a lot of this rainfall gets captured, shunted. And so what we're seeing are first and second order streams are dry. Now, what's really cool is when you look at USGS topo maps over time, if you look at like one from the 1950s, that's a permanent stream. And then 1970s is permanent, but then we look at more recently, this is all now impermanent streams. And in part, we think it's due to the ditch moving the water out of the system. But we haven't looked at that specifically, but it's definitely a common pattern that you'll see first and second order streams dry a lot of the time. So in more depth, this is still Doolittle Creek, which feeds down, is near Candor, and feeds down the Susquehanna. So the first graduate student was Juan Diaz-Robles. We had 8 different ditch monitoring stations and also the outflow of Fairfield Creek, monitoring 10 storms over that time. And we know how much rainfall was coming in and how much through the true tracks, how much water moved through each ditch during each event. And on average, each ditch captured about 51% of the rain in the ditch's basin. So they were capturing and shunting a lot of water. Modeling, upscaling to the whole watershed, because we had mapped the whole watershed, all the ditches, we knew all the ditches, all the drainage basins. Of the total stream flow, basically per storm, about 20% of that was coming from the ditches, okay? Then independently in Paynes Creek, later than Kim and Brian were working up near Lansing, we estimated 22% of the total stream flow in spring event and 29% in summer event came from the ditches, or being moved to the streams and actually contributing to stream flow. Brian, who's a phenomenal modeler, took it further, modeled his work all focused on Paynes Creek watershed, and after doing the model, he went out and put in true track water samplers both in the ditch, here's the ditch, and in the stream, and then modeled what the total amount of water is and what was the contribution of the ditches. And so this is an example of a spring and a summer hydrograph. The green is actually the ditch, how much water was flowing in the ditch over the course of a storm. And the solid line is the stream without the ditch, and then the dotted line is the stream and ditch superimposed. And so in spring, the ditches contributed to an increase in the peak flows of an average of 78%. And in the summer, total flows 57%. In the summer, actually increased peak discharge up to 300%. So that, and it's coming in mainly during the rising limb of the storm. So it's coming in, it's pushing up the stream heights. That's the flood. Now these are small streams, second and third order streams, but nonetheless, it's pushing the water up. That's definitely contributing to flooding there. We looked at what kind of movements of materials are going on in the ditch, and this we started with Juan, and basically using the ISCO, and this is just the duration of a storm in hours, and here's the total sediment load at different times, and the blue line is the discharge during the storm, and not surprisingly, very high levels of sediment moving in the ditches. One of the core parts of his thesis was how important was the scraping they were doing, and so as you went from a vegetated ditch to a bare exposed ditch, not surprisingly, the concentration of sediment, and this is the peak concentration, increased in the water. And it's just a no-brainer. There it is. There's a scraped ditch and it looks like a milkshake because the water rains, all that water erodes, all the sediment's moving out. So they're definitely, if they're scraped, they're a source of sediment, but they're also, that they themselves are a source, but they're also capturing erosion from the lands adjacent to them if they're exposed. So they're both a source and a conduit of sediment from adjacent lands. So we knew the concentrations during a storm. The maximum recorded in this Doolittle Creek was 38.3 grams per liter. On average, it was about 65 kilograms per storm day. This total ditch network, on average, was 7% of the sediment we found in this fourth order Fairfield Creek could be attributed to the ditches. We upscaled, because we haven't mapped all the ditches, we knew how many were scraped, and using the miles and all the total lengths, we were able to come up with an average value. Paynes Creek watershed, actually we had this all agriculture. This is not actually Payne's Creek, but it again shows you this. This is actually about 2.5 miles of scraped ditch with all the sediment moving for it. It had higher, maximum recorded was 52 grams per liter, and the total load per ditch was 540 kilograms per storm day. We had some really high numbers. I actually had it up there, 31,000 kilograms for one big storm. I thought, I gotta check that again. Is that possible? We calculated again and again, but it's like, wow, right. We've done some work looking at other things that move through the ditches. The one I want to point out here this is sodium, total load of sodium and of calcium. They're really high, 11,000 kilograms. So we picked that up as de-icers during late April. And phosphorus, we've done a little bit with it. This is, again, the Forest Doolittle Creek watershed with an average concentration of DLE of dissolved of 0.015. Total load dissolved and sediment bound of about 2.5 kilograms per storm day, which is 11% of the phosphorus load in Doolittle Creek. We did a back of the envelope. It's just rough, and this is one of the places we still want to do a lot more work is what's this mean when you upscale to the total system? We had looked at 3 storms between 2005 and 2006 where we had also monitored those, had information, it was at the same time period from our Candor site, and we had sediment loads in the Susquehanna River. And we just multiplied basically our rates per 1,000 meters of ditch by what the total length of ditch roads were, and basically came up with an estimate that of the actual documented sediment coming out of New York State in the Susquehanna River during those 3 storms, you could attribute from 0.6 to up to 11% of the total sediment, suspended sediment, and 15% of the phosphorus could be attributed to the ditches. And it's a phenomenal amount of sediment. When you guys see these, I mean, you'll start watching ditches. It's very addictive. There's incredible quantities of sediment moving out of these. So it's a key part. We haven't looked, again, we haven't really done a whole model. We haven't done a model of this scale. Don't know really what happens in the big rivers. Don't know what it could mean for total maximum daily load controls. We might be able to, we think actually this could be a way to start controlling some of the things you have to deal with phosphorus and sediment for the new Chesapeake Bay TMDL rules. All right, so definitely ditches are both a source of sediment. They're also a conduit of sediment and other contaminants, and this is Taganet Creek. And I know this is coming. I know the ditches. That's where that's coming from. I know you have to watch those. All right. Then we looked at ditches as conduits of microbes, and our hypothesis was there's an awful lot of ag land up in the headwaters of watersheds, sometimes miles away from like a drinking water system. They spread manure. Does that really, like fecal coliforms, does that end up down in the drinking water? And so that we got some funding to look at that. This was Kim Falbo's graduate work, and we looked at 4 separate little watersheds to up the feed into Cayuga Lake and 7 ditches. We had 4 ag fields that had manure spread on them, 3 that were forested as kind of a background level. Monitored using the ISCOs and ice to keep it cold, but we're looking at fecal coliforms. 54 days, 20 storms, the water samples. And thanks to Dan Buckley in Crops and Soils, right? And Peter Burkholz, we had this really nice, simple technique to look at and quantitatively count E. coli. And so we could actually count the amount of E. coli moving in the water. So what did she find? This is July of 2008. Here's January of 2009. This is one manure spreading date right there. It's about 2-hour occurrence. This is one ditch. The E. coli move in the storm. We had actually up to 250,000. That's some really high numbers, but it's way above any standard for EPA. And then over the course of that storm, it stays high, but keeps still there. And then there's no water flowing in the ditch for weeks to months almost. And as soon as we have the next rain event, there it is again. So that E. coli continues to move, gets lower and lower, and then manure spreads and it spikes again, and then it continues into July. And so basically, they put it out for 2 hours. The ditches are right next to the farm fields. The manure, the E. coli, move into the ditch, and it's still present for weeks to months and moving down in the water. This is all the water. We asked the question, well, what happens in between those rain events? Is the ditch a reservoir? Is it a source? Turns out, this is way after it's rained, 10 days after it's rained, and we have soil moisture content and things like that. But basically, there are still viable E. coli in the sediment. This is all dry times in here. I mean, radionet dry, this is dry, and we have E. coli living in the sediment. We don't know that they're reproducing or whether they've lived long enough. Don't know that. So is it a source or is it just a reservoir? But they can definitely move again when the ditches flood. So definitely they are a conduit, and then Brian Buchanan's done work since then for us, figuring out the timing, and basically within hours to a day. Even though these headwaters can be miles away. People in the headwaters don't think, oh, what we do is affecting their drinking water, 20 kilometers away, but they're so efficient at routing. And in particularly, when they put in tile drains in the farm fields, so this is the roadside ditch, basically it rains and dunk, 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 and hits the stream and it's down there within hours. And so these head straight to our drinking water supplies. What's really kind of, starting to think about it, when it used to be before you had roadside ditches in, and remember that hill slope that led down to the stream, if you applied manure, there were miles long of soil that could filter out those E. coli. There was tons of distance for that slowly to process through all the different ways that they, sun kills some bacteria, then things bind to the soil, and there's food webs that eat up bacteria. But now, we put E. coli fecal material on the surface within 3 feet. It drops, it hits this tube, shunts to the ditch, shunts to the stream, and it's down. Only 3 feet now is expected to process all that viable material. And so that's pretty short-circuited the entire stability of the system. Okay, all right, the last piece, the piece actually I'm the most excited about, we have the least data, and that is bed load. So basically, this is one storm event's bed load from one ditch. And what we saw, there's large quantities of gravel, rocks, and other bed load that moved. Now this is the June 2006 mega storm event, the one that flooded the Susquehanna. So it's not typical, but this is a meter deep of rock that moved in the ditch. This is the ditch, that's our actual study thing buried under there. And what happens is, as soon as it hits the stream, it dumps out and forms a delta. Okay, and that we definitely have that documented. And so, think of this as, this is actually the Adirondacks, but normally streams have a sinuous pattern, a natural geomorphology that controls the pattern of the where riffles occur, where pools occur, the amount of curvature that occurs, and the energy of the stream determines all that. What happens is these highway guys just take there's the stream, let's take the ditch right to the stream. And it could be right here. They dump a ditch right there. Now think about what they've just done. The natural energy of the stream is eroding this way. You can even see there's a former curve of the oxbow or a little tiny bow of the stream. Instead, a delta forms right here, and there's this high discharge velocity stream dumping in. The stream has to go around the delta, and the velocity of the incoming ditch water also starts to erode this bank. There are 94 of these in each of these small watersheds, everywhere in there. The whole system is starting to erode. That's my hypothesis, that these streams are totally out of disequilibrium because now these ditches are chronically hitting them with large volumes of water and bed loads that are growing. So, working with an undergrad along the way, we did start to get at this issue of geomorphology. We haven't gotten a grant funded, except WR was kind enough to fund this one, where we actually looked at 30 meters above the ditch, 30 meters below the ditch. There was no other, this was a first order, so there's nothing else happening up there. It's just a stream with a ditch. And not surprisingly, so what happens is this is a true first order, but as soon as you add this ditch in here, it changes the hydraulic radius. In some cases, this is bank full width, for example. You would imagine more flows coming in, it erodes the ditch wider. Or in some places, it incisors it deeper. But the overall hydraulic radius immediately below the ditch is way bigger. And that's cool because, like I said, the first orders, there are parts of them are drying out, but they're so big, they only are big enough to handle storms. That means they dry in between. That's what we're pretty sure is happening. These are storm-driven geomorphology where our streams are out of whack, totally out of whack. They're driven by these mega flows that occur, and then after that they kind of dry out because they're so big, they're not shaped properly. We also found some changes in the grain size distribution, and what's happening is, and this is really easy to see, they use gravel along the shoulders, and if you ever notice, outside your house, the highway guys will show up every other year and put more gravel out. Well, where do you think it goes? It ends up in the ditch and washes down. That's part of what the delta is, and it's affecting the rain size distribution downstream. We don't know further than 30 meters, but definitely once you start affecting things like substrate, you're affecting invertebrates, ecology of the system. So there's a lot more we can do with this. We haven't gotten a good grant to fund it yet, so it's kind of piecemeal, but to me, it's actually the most exciting part of this whole thing. All right, so what do we know so far? They definitely capture rainfall. They shunt it rapidly to streams. They definitely increase peak and total stream flow, so they're contributing to flooding. They decrease base flows. We have a little bit of data to show all that water moving out is making the streams drier, but also lowering the water table. We have just a little data on that. They do transport large quantities of total suspended sediment, transporting microbes, and some evidence on impacted geomorphology. So they are significant. They are significant but overlooked transformers of our entire watersheds. So what do we do about it? Oh, where are we going next? So the fun, exciting thing is actually we're now starting to get into the nitrogen cycle. So this is our new part. Lauren is going to be our PhD student working. She's focusing in suburban landscapes. And then Roxanne is actually going to work with me and some other people, and we're going to start looking at ag ditches. And so between the two, we'll have a lot of the landscape. And we're all thinking there's a lot of nitrogen coming off from septic systems, could be fertilizers, could be farm fields. All of this is the channeling through these ditches. The ag channels through the ditch. And so it might be a control point where we could hopefully affect the nitrification. That's the exciting part to me, that maybe you can, when you know it's all right there, you can maybe manipulate that system and reduce the amount of nitrogen that goes to N2 and push towards N2. I have no idea, but it does seem like a definite control point. One thing, while I remember it, so I'm talking to highway guys, soil and water is the one who helps them do all the tiling in the farm fields. And their typical strategy is, well, you tile it, you take it to the roadside ditch. And so all the tile systems lead and drain all that water straight to the ditches. So it's definitely something we need to focus on. So in parallel, that's the beauty of being at an extension university. If we were at Harvard, or they don't do extension. And so you could get this published in scientific journals, and nobody ever used it, would ever see it. But because we have to try and help solve problems, we have to get out there. And so we have worked with thousands of highway guys, mainly through the Cornell Local Roads Highway School, annual highway school. We have fact sheets, we have presentations. We've had dozens of invited presentations of video conference at the Center for Watershed Protection. And so we've been focusing on building awareness for a lot of years. Talk to local governments because they had to deal with that EPA Phase 2 stormwater regs. And these are the things we tell them. There are things you can do better. And that is where green infrastructure meets blue infrastructure. So on the web, the Chesapeake Bay says blue infrastructure is the natural water system. And so this is all about the green infrastructure of ditches and doing a better job and making it to blue infrastructure. So hydroseeding, you'd think they all do it, but they don't. And they were limited on equipment. Some are limited. Sometimes they actually put this out in late September. This is one of our study areas, and it didn't have enough time to grow. It died. And the biggest problem with a lot of these, like bioswales or things where they hydroseed, there's no follow-up. They don't water them, they die. Studying Washington State, 90% just didn't work because they didn't follow up on it. I think there's a great promise for check dams. A lot of the sediment movements due to erosion when they get incised. And so if you can slow the velocities down, that's really good. Organic matter builds up behind them, and I think they might be, and slows water down, they might be a key way, I'm hoping, who knows, to deal with the denitrification issue, but we don't know yet. These are bioretention swales. These are the big green infrastructure things. Maybe they are a strategy. You could change the ditches and basically replumb them so there's more filtering that occurs, slows some of the water down. Working with David Orr, so he's been great about all this. He's the director for the Center for Local Roads, or Cornell's Local Roads, great program. He's an engineer, and so we actually said, well, what are other things you can do? Well, ideally, we don't want that water leaving the system. In theory, you could put pipes under the road that carry the water from one side to the other, under drains. The shoulders are a big worry for me. The best we can come up with is permeable non-gravel shoulders, but incredibly expensive, but may be a solution. Infiltration basins. All right, so like hydrant seeding, we can reduce that sediment a lot, right? You saw that curve. If we can get those vegetated, the amount of sediment moving could drop to really low, 0. But that still means all the water's going to the creek. And my big issue is we have rain, don't get rid of it, don't race it out of here, save it. And so you have to disconnect the ditches from the streams. That's my big thing. And so infiltration basins, something that the rain all goes there, all the ditches go there, that would be a strategy where how you guys can just disconnect them, put them into the infiltration basin, and it slowly heads down to the groundwater. It's not a perfect solution. That stream's still dry further up, but it's better than getting rid of it. Constructed wetlands have a lot of benefits, of sediment removal, phosphorus, slow the water down, keep a lot of it in the system. There's some beautiful ones. I mean, they're attractive. And actually, a study up in Monroe County showed that constructed wetlands for stormwater, if they were done right, increase the value of houses around the edge like a lot. People like to look over wetlands. This is actually the one over on Warren Road. So, and until recently, I thought infiltration basins were the answer, but now some of your preliminary work Lauren's doing suggests it may become a denitrification source. Maybe they're not as good as I thought. It's like, oh man, I've been talking infiltration basins for 5-7 years. So what's the deal? I mean, I have literally talked to thousands of highway guys. Why aren't they doing it? Because we've made some headway. The New York State Department of Transportation has a drainage group. They changed their vision statement to deal with ditches, and we put input to the DEC manuals for stormwater. Some little towns have adopted rules, but overall, I thought more would happen. So it's really this issue about green infrastructure. Is it being adopted or isn't it? What's happening with green infrastructure? We're all saying it's the answer. You know, green roofs, rain barrels, rain gardens, infiltration basins, that's the green infrastructure for water. Well, there was this cool study, which I think WRI paid for, right? Emily Vail and Andrew Miller, very nice people, and they did an inventory, surveyed a bunch of landscape architects and engineers. What were the barriers to green infrastructure adoption in the Hudson? And there were 4 main types. So not enough technical knowledge and experience in the development community was key, and it was undervalued by the development community. So that issue of increasing awareness and more information is key. Lack of design standards, lack of materials. Funding was definitely a key part of it, but this one down here is important. Community is not convinced about its effectiveness. And so, again, that's something Todd showed you all last week, where they're trying to start to figure out, what do they do? Are these things working? Because there's just not that much out there. And usually you get money, so we have a grant in to do proposal to do Chemung County. There's 20 miles of road they want to put check dams in. We're going to do demonstrations and then monitor. But if you can get a year's worth of monitoring money, it's usually the last thing, you know. So there's not a lot well known. For us, David Orr did an engineering economic analysis of all those options I showed you. So hydroseeding, check dams, crossroad under drains, infiltration basins, and permeable pavements, all different options. What's it cost? Because the highway guys, that's the question. Well, what's going to cost me? Why should I do that? You know, and it ranged from, if you just leave it as is, it's about $2 per foot because they still maintain it. You see that it's really cheap, and they share hydroseeders, so at least they can hydroseed. But it ranges up to about $20 per foot when you start putting in pipes and all of that. The most expensive is permeable pavement, $500 a foot to totally repave. So there's a full range of costs, and it really comes down to how much you care about the water quality downstream. I mean, water is worth so much out west, and we waste so much of it. You know, it's just like, gosh, guys, there's a lot of water leaving that we could save. So where are we going on this whole part? Tony, right here, is this graduate student who's actually going to do a survey right now of our highway guys, working with David Orr. David knows personally, I think, all 999 town highway superintendents. I swear to God, he knows every one of them. And so we've just sent out the first part of this survey, working with Shorna Allred, who does human dimension surveying. We have this check dams demonstration, we hope to start over in Chemung County. We'll see if we get that. And then Kathy Boomer was a grad student here. I don't know if any of you guys remember her, PhD student. And she's now on the Science and Technical Advisory Committee for the Chesapeake Bay. And so she said, we need to do a whole program on ditches because there's all these TMDLs. And can the ditch management play a role for the Chesapeake Bay watershed? I have been trying to break into the Chesapeake Bay for the entire time. And so we have put in a proposal with a lot of very interested people. And so hopefully we'll get that funded and we'll have a workshop within the next year. And so that's the overview of all of it. And so I'm convinced, not everywhere, but many places there's rain and we're wasting it, we're throwing it away. And we need to replumb the system and save that water. And then you have it later. The water tables will be higher or you can save it in other ways. And I think it's a strategy. It won't solve all the problems, but it will definitely help. So that is the overview. You guys have questions? When you start washing dishes, let me just tell you. And I'll take any pictures of anybody goes to another country. I want ditch pictures.
So why do the highway staff actually clean out the ditches on a regular basis?
So the deal is they've been doing this for 100 years like this. They are not, many times they're just high school educated guys. Their town superintendent in your state is an elected official, sometimes with no background. It's very interesting because I'm trying to look at the governance system. They're about equal with the town supervisor, but work independently. Nobody tells them how to do their job, and they've just been doing this practice forever. In our state, people, one, it's part of their regular scheduled activities through the year. They scrape the ditches, they fill potholes certain times of the year, they have a backhoe. And when a lot of times they'll tell, I have talked to tons of these guys. Like, okay, well, the guys have nothing to do, go clean out that ditch over there. And the other driver, Mark Wasaki, just told me, he said, hey, I want you to come write a letter to my town. He just said this as I walked in the room. Why don't you write a letter to my town superintendent and tell him that he needs to scrape out my ditch because it's flooded my basement. And I thought, oh my God, it's too perfect. And that is the truth. People call and they're an elected official, my basement's flooding, and they get a scraper out there and they clean it. And that's the reason why. And they tend, according to David Ford, way over ditch. They get deeper and deeper. I didn't show you all the pictures, but I have some, they're like 5 and 6 feet deep. It's just amazing. I have pictures of cars in them like this, they become an accident source because your car goes in there and you start to wonder if you're going to survive, So yes, they tend to scrape a lot.
So you've looked at ditches, I guess, around the U.S. and around the world. And are there places that, how long have you been studying kind of the water flow impacts? And are there places that are more receptive to the suggestions that you had to capture the water?
Okay, so the facts are, this has been going a long time, but it takes time to build credibility up. And then we've just really got some of our papers published. Brian did a great job getting a lot of work done, where you have the scientific credibility. So it's still building. Most people don't even think about ditches. I didn't even think about it. They're just part of your landscape. That's how ubiquitous and how background they are. The highway guys sit there and go, oh wow, we never thought about that. So China, the guys who work with over there, they believe it. We've got some proposals in to look at it over there. But nobody knows about it yet. We haven't gotten, it's still, there's a ton that has to be done.
Yeah, a couple of questions. The mapping thing I could see is a real challenge because just in my house where I live, there's ditches and the natural stream flowed behind my house, and you can still see where it was, but it's not there except if you have an incredibly high rainfall, then you wouldn't see any water flowing there. Right? So even if you took like a GIS system, you'd think a stream was there, but because it's been rerouted by the ditches, so I can see that. That would be. Brian
did it awesome. I was the one postdoc. This guy's amazing, but he actually burned in the ditches next to using LiDAR. But even if you do get the ditch network in, it's where they dump.
Right.
So we've actually had part of several of our watersheds get shunted. The water's all shunted to another watershed via the ditch network.
And then knowing how you've changed the stream network too, it seems like that would be tough to get it.
Yeah, and that geomorphology, I'm convinced, is the key. There's so much sediment moving in the ditches. They're all eroding. All the banks are eroding from these constant inputs of high velocity flow during a storm. we haven't even touched what has to be looked at for that part. It's huge.
But then the other issue is, it seems like, at least from local experience, you may have these kind of, you kind of develop up a watershed. A lot of development takes that place like that. And so maybe initially stormwater drainage was in pipes, but then you got to a point where then they just have a lot of housing developments where there's just open ditches. But then, like happened in the town of Ithaca, then you go beyond that, and then you're going back to pipes, so that you have areas that are piped, both roads and houses
I
that
haven't
are
touched
then
pipes.
feeding
He's
in.
willing to touch pipes. I don't want to touch it.
Right,
You can't follow.
and then they feed into ditches.
Yeah, I know.
And then the ditches feed back, and it just seems like it's
It's a mess.
right.
6 Mile Creek, we actually started mapping all of that, but part of it just become the stream system, and then they back
Right.
out again. So
But it seems like in a lot of people, highway superintendents' mind, the alternative to ditches are pipes. That's the alternative to ditches. It's not all these other things.
Right, I know that.
Yeah.
that's what we have to educate them.
Yeah.
Well, see, that's
Which
what
seems like even a worse direction to go in.
right. I mean, it's replumbing, but it's all about what's happening to where they dump it. It's like, well, if you care about water, I mean,
Right.
fish habitat, all that gravel, the fact that it dries out, the incredible velocities. It's all about, do we care enough as a society to say, especially now that water's getting more valuable. It's like the highway guys have to be part of the conversation, and they're not. They have never been included, and so that's key.
Right. And the other thing, but although talking to our highway guys and going through that, and when ours are appointed, not elected, you can get that changed in New York State.
Yeah. Okay.
But a town has to consciously, change their code
Right.
to do that. But our guys just say, but that's just the way it is,
Yeah.
because
That's what I'm fighting.
Yeah,
This-
it's
this
just the
boat
way
that's
it
been
is.
going that way. This
Yeah,
giant,
right.
you're trying to turn like this, but the awareness is it. I mean, I've been talking to these guys I'm now getting calls from around. Hey, we come talk to our town from across. The awareness it's rising, and so like the Hudson. There's David Wixon.
right.
He's starting to do. It's happening at New York State level, and then some in Pennsylvania. So it's growing. I
Yeah.
actually think, but you got to keep at it.
Yeah.
It's going to take a
Yeah.
lot more work.
But the one other thing that impressed me was all that manure. I mean, because you talk about septics, you have these little septic tanks, there's leach fields, there's all this stuff supposed to be going on with septic. But when you think, in a lot of situations, what would be the contribution of septics compared to all of that cow manure?
And it shuns straight down there with hours.
Right. I mean, it's
And
like
weeks
we're putting
later-
an awful lot of effort maybe into not the main waste problem.
I'm saying, when we went to the USDA, you go ahead of time when you get the grant, and a bunch of people are sitting there, and I'm like, it's got us some money, I don't know anything about people develop forms, so you go, and 3 people are all saying, well, we could never find them in our system, it took us weeks we had to concentrate them, oh God, we're never gonna find any. We get out there, and it is we have so much moving, weeks later, I mean, it's dry, it's hot outside,
And they're still-
months later, and it's still moving through the ditches. I mean, they are conduits for fecal forms. It's like holy cow, it's going right to Cayuga Lake, guys. Don't drink that water. See, that's good news to me. This is doable. We can change this. This is not, we got to get CO2 under control. I'm thinking, who's going to do that? That's not toughie. We can do this, I mean, this is so doable to me. This is like, hey, people in California, how much would they pay for the amount of water we throw away? Think about it. One company comes in and we say, you got all the water. Can you heal this problem? Yeah, I'd be doing it. Yeah.
The goal of the highway crew is to make the water go away, right? And so, like you talked about the guy who just wants his house to not flood, and so could you please come scrape my ditch?
It's down there.
And so, and I'm over in the planning department, but so it's how do you help the water go away quickly without, while maintaining the ecosystems and then not disrupting people's lives. And so how do you educate our communities, and how do we manage it in a way that people aren't
Being negative.
inconvenienced by
Right. Well, that's a key.
water?
So, like, talking to the town highway guys, a little bit we've done, this is why Tony's gonna do this whole survey, but one thing they told me is, look, we don't own those ditches. Town highway guys don't own them. They have the right of way. That means the landowner owns the ditch. Because I can't go reshape that ditch so it can be mowed. You're gonna get ticked off. There's a whole education process that has to go to the landowners, that, hey, you're part of the stewards of the land, and this is our water, and you're gonna run out of water, we've been doing it for 100 years. Replumbing is not gonna be easy. It's gonna take a lot of different stakeholders, top-down mandates, incentives, education, it's gonna, and, I mean, that issue of basements flooding is key.
Right, and Mark, well, he does live in Wyland, but I mean, in Dryden, he's right across from a 10-acre wetland.
Well,
But part of his problem is, because part of his problem, and this is what happens, other little development takes place.
right,
And so all of a sudden, you've been in a certain way for 20 years, and especially around here, it's common, and so all of a sudden, water
is being rediverted, right,
Yeah.
down to you, right?
But I'm assuming that some of those ditches also have culverts associated with them, and then you mentioned check dams. So I mean that at some point those have to be flooded, right?
All right, culverts going to streams, you mean, like when where the stream goes under the road or the
Right,
ditch goes,
right.
right, there's totally that issue, and then Todd's actually doing some nice work in the Hudson, which you guys may have paid for,
Yes.
to about resizing culverts,
Right.
so there's a whole piece to look at that.
Which brings up legal issues, because
Right.
those actually prevent flooding further
Right.
downstream if they're undersized.
It's just, you gotta change the lens you look at the landscape in, and that's why I actually work a lot with landscape architecture.
Well, and
Because
looking
there's
at things at a
stewards.
watershed
You have
scale.
to look at it at the
Yeah.
watershed scale, and you have to say, how much is that water worth? How much is it worth it? I mean, when there's so much sediment moving, we are just ballparking these numbers. The amount of sediment is phenomenal, and it costs money to clean that out. I mean, to have drinking water. So it's like, well, give me half that. You give me a third of that money, and I'll reroute these ditches, and you won't have that problem. You know, I can cut it down, and cut down the erosion in the streams. You know,
Yeah.
to me, it's all fits together, but it's like this is doable. We got a solution here. You know, yes.
So I guess my question relates, my comments relates to what's been said. It seems like relatively easily you could at least change the functionality of the ditch by working with landscape architects to design vegetation that would at least.
Yeah, we're doing that. We're trying some of these things. Yep.
Here in this region, but when you were sort of talking more broadly about areas where you want to save water when you need it, I mean, the Corn Belt should be a wetland, and so
Right.
you
That's
can't
true.
store that water.
Right.
I mean, like, they want to get rid of it fast because if you store it, then they can't grow their corn. So,
Right.
do you see solutions for places like that, or is it really limited to our topography where we can seriously think about replumbing and keeping the land use that we're used to
Right.
in terms of housing and agriculture?
Right. So you're right. The Midwest was all on giant well, and they ditched them, but their ditches are 25 feet deep. And so work on ditch. When you read about ditch work out there, they're focused on the bottom of their ditches, where they realize that they have two different levels, a terrace level and a low level. That it does all these good things. Basically, it acts like a little stream at the bottom of this giant ditch. So there are things they can do with those big ditches to improve sediment movement and stuff like that. To me, again, it's how much of that landscape you can replumb that landscape. You can fill in those big ditches at certain lower locations, like the Wabash River in Ohio, and restore those large floodplains and get back some of that flood retention. So the Mississippi isn't doing that incredible thing. They've taken down. I mean, it's amazing when you start looking at the levees along the Mississippi, and they're doing buybacks, the buyouts. So when the big floodings occurred, FEMA has paid $2 billion for 40,000 properties as buyback, where they then convert to green space, which if you then got rid of the ditches and stuff, they would become more functional as floodplains that help do water storage during events. So some of that is possible. I'm basically an ecologist at heart. To me, there's too many people, but I'm all about compromise. The truth is, you can't take the whole Mississippi back. You maybe can't even take 10%, but you can take some. And well, you should pick judiciously, say, no, we need to restore that area and get rid of those big ditches. But in those flatlands, even Delaware's ditches, so I've been looking at Delaware, they're different when it's such flat topography. They tend not to be connected to streams. They tend to be the surface of the water table almost. And so they kind of go up and down. They do move water, but it's not this really intense replumbing that we have. But they still are draining the landscape. So you'd have to look at it as a different type of replumbing.
You mentioned the sediment load is highest is about 20%. From
The quick estimates we did for the Susquehanna were up to 15%, 11% sediment, 15%
15%,
phosphorus.
and then a significant amount of water also goes in. Now, if you were to look at it from a legal perspective, I mean, do you think, have you come across instances where someone could argue that the Clean Water Act could apply to the ditches?
Yeah, so actually I worked with Keith Porter a little bit. He had a student put out a small paper about policy association. I was actually in contact working with EPA, Nicholas Quack, for couple of years, they actually start to look into that as being connections basically of the stream channel network and the navigable waterway. There's so many gazillion miles that the management of it, the policy implications were beyond what they would even be willing to tackle. And so they just didn't, just went off the table. There was a lawsuit, there was a law, actual, I can find it, it's been a while since I looked at it, but where somebody argued the ditch was part and therefore the flooding was due to the ditch, you know, but there, EPA was not picked up. It's just too big a problem and they're not willing to take it on.
Can you talk a little bit about the infiltration basin? That you say the infiltration basin is, you say it's not, maybe it's not the best one, but for me, I think I'm interested in it. What is the negative thing?
All right, I'm not an engineer, just so you know. I'm an ecologist, just like Alan, right? So I don't know as much. In fact, probably Lauren can talk. She's been in more of them than I am. The ones on Long Island are these big pits, and the ones that they put all over White Marsh, down near Baltimore, Maryland, are again these very deep pits. So the ditch, stormwater runoff is routed. Even Susan probably knows what I mean. Routed to a basin. All the ditches would connect to the stormwater, and it's made so that the water builds up, but then it gradually infiltrates. And then there are spillover valves and pipes and things, but basically the intent is the water sits there and goes back underground and recharges the ground table. There are what are called detention ponds, which if I understand them correctly, grab all the water and then slowly it moves downstream, but it slows down so it's not going straight to the stream causing flooding. The infiltration basins, construction guys' development is the reality of it. They're going to put up this big complex of buildings, make a ton of money, and you're telling me I have to take a chunk of land out where water goes. Well, I got to put a house there and make money. Instead, all right, instead of making it big, wide, flat, constructive wetland, which would take a lot more space, the deeper it is, the smaller it is, then I don't lose as much money. So they follow the guidelines, but minimal, and so many of them have fences around them because there's liability issues. Right. Somebody falling in, they have very steep sides, they're not safe. They can be, the stuff that Lawrence were working on with the Todd is looking at, are there metals that build up in those because it's runoff from roads? Salts, are they toxic? I'm worried about them becoming sinks for animals, like amphibians will go to a wet, low area and then live there, and then it's picking up metals. Are all our amphibians going to end up there dying? I don't know. So I thought it was a better solution because the water didn't go to the stream and out without being gone. It recharges the groundwater. But they're all compromises. You know, the truth of the matter is we shouldn't have any of that out there. You know, these are compromises. You get some gains from them, you get some disadvantages. It might still be a better solution than dumping the water out. That's the best thing. And they all need maintenance. Everything that we do needs maintenance. So they have to scrape out the bottom of that. They're engineered systems. They're not natural systems. So they need work.
Yeah, because,
Go ahead.
Sorry.
No, go ahead.
Because I think in Indonesia right now, in Jakarta especially, the government tried to make a regulation that every house have that kind of thing. So the rainwater that is fall down into your roof, you catch that one and put it in the filtration basin and it goes to the.
Did you say Jakarta?
Yes.
I just saw a whole presentation on Jakarta.
Yeah, I mean that they are trying to do it right now.
That's amazing.
Yeah,
I mean,
so
the rivers
that's
are
why
right
what is the negative? I don't know.
there. We need to talk, because now I understand Jakarta. I mean, it's a
Yeah,
river
it's
with
still,
some people
it's
living
still
on the
funny,
river.
but it's trying to.
It's amazing. And there's there's no sewage system at all. The
Yeah,
river is the sewage system.
especially what do you call it, the catchment area in the what do you call it, the highway.
Yeah.
It's been totally great for houses and something like that. And it's become, even though Jakarta is not raining, it can be funny. So
Yeah.
it's
All right,
fun.
we got to talk, because I've seen those rivers are lined with plastic trash bags. I mean, it's just phenomenal amount of waste. They got issues
Oh,
that we could talk about. All right. Yeah.
I was curious about the reception you mentioned you received in China. So I just spent a lot of time in Yunnan province, and I was impressed by how they build these like very deep stone drainage ditches. So I don't see a way of making them more biological anytime soon, and it just seems like they would get incredibly loaded with sediment from all of the extremely tilled steep slopes there. So I'm just curious what parts of China are actually
We just have to be working with, it just happens to be a Humphreys fellow that came here, Dr. Shang Xiao Li, was responsible for restoration behind the Three Gorges Reservoir. He came as a Humphreys fellow here. We're now working with him, and he's bought into the ditch thing, and so we're gonna start a project there to start trying to do this documenting. And there, what's kind of cool is the ditches lead into the rain. The ones we're looking at lead straight to the rice paddies. So it's a ditch rice paddy plumbing. It's kind of very cool. But anyway, so we're just starting. It's huge. I don't know. Anybody? Next year will be Lauren giving this talk. And Roxanne and I, we're at the ag, and we're gonna have a little complimentary show. Yes.
I know that I missed it, but do you know how much water that's going into dishes is coming from the roads, and how much is coming from the other landscape, if using the watersheds that you've been mapping?
So off the top of my head, it's like 0.7% of the, on average, of our 7 watersheds is road surface. 22% is hill slope draining to ditches. So in comparison, it's 20 times more hill slope contributing than the half of a road, because it's only the top half that goes to the ditch. Interestingly, the amount of water when we calculate how much is in the streams, where is that? It fits pretty much with what we see as the drainage basin. Where is that? Hang on a second. Yeah. So when we see 20%, 19% of the stream flow as being due to the ditches, that was in these cases almost exactly what the ditch basins were. So it's really the basins that are driving, the basins that lead to the ditches that are all that water significantly affecting the stream. Did I answer it? Anybody else? Anyway, green energy, this is a good thing, guys. This is doable. So these are solutions, okay? We gotta look for them where we can get them. Thanks.